Okay, hello. So the title that I gave myself was Field Observations of Material Changes in the Shallow Subsurface. So we have seen during the week a lot of methodology ranging from noise sources over interferometry, monitoring techniques, and scattering. And I wanted to give you some examples that I think are important to understand what range of processes we can observe with this technique, and mostly focusing on the shallow subsurface. But I restructured that a bit. In the first part, I will connect a bit to Ludwig's talk, because we had the question of how would actually the sensitivity of our monitoring depend on this scattering structure that is sensed or that generates the Coda. So I will give some insight in that in part one. In the second part one, I will go through some field observations, but I will be very quick because we've seen a lot of that during the week already. And in the second part then, I will talk about hydrology. I think that's quite a nice topic because we can really do something useful with our monitoring technique, because water resources are important for all of us, and this is work that is done by Luc Elian, a student I'm working with, and the first part is by Turzang. So let's start with this. Using radiative transfer theory, we can model the intensity propagation. That's what Ludo described. So it describes the flux of energy through the material. And it's actually resolved in all directions, but that's not so important. What is important is that the total intensity, which is the integral over all directions, can be measured easily in seismology as the envelope of a seismic signal. So that's the energy, the seismic energy, basically, that propagates. And here on the left side, we have a simulation that is excited by a P source in a scattering medium with 5% fluctuations. And what we see here is the S energy. So now you might wonder, how does the S energy reach to here if the first arrival of the S energy is actually here? So that's just because we have a P source, and on its way, the P energy is converted into S energy, and then it's pretty fast here and arrives as S energy before the actual S phase arrival. That means in the P coda of an earthquake, for example, there might already be shear wave energy. So this is obviously a homogeneous medium, or a uniform medium, because the heterogeneity in the background is uniform. So if we have heterogeneity distributed like this, which is we have fluctuations of the velocity of 5%, or velocity, density, and so forth, of about 5% in these bluish areas. In the dark blue, we have 9% fluctuations, so the heterogeneity is stronger. And here we have more homogeneous materials that only have 2% of heterogeneity. And then the energy density looks like this. So we have in these areas of strong scattering, we have an accumulation of scattered energy at that moment in time, because we still have a P source, and the S energy here is generated more efficiently than here or even here. That's why we have an accumulation of energy here. So now, thinking of how that would affect our measurements that we do in the Coda, it's obvious that they will be more sensitive to these areas because we have more scattering in these places, and the energy kind of stays longer in that areas, and therefore senses these areas more intensively. So we did an experiment, and we calculated the travel time sensitivity kernels, which are important for interpreting lapse time changes in the Coda. In this model, where again, we have an area with less scattering, an area with stronger scattering, and some intermediate background heterogeneity. And I will not show you in detail how that works, how these kernels are calculated, but the bottom line is that this kernel that is describing the influence of the P wave velocity on the travel time from an S source and sensed S energy. So it's quite detailed information that we would need to really use this kernel. But in fact, it is somehow included in the overall measurements that we will do. And we indeed see that from a measurement that is excited here and sensed here, the area where we have stronger scattering is indeed more influential on the final measurement. And when we look for the influence on the shear wave velocity, the heterogeneity or the difference between these two areas is in fact a bit weaker, and we can talk about more details of this if you are interested in. The bottom line is that in fact the scattering structure is important for interpreting how our measurements are sensitive, and by now there's some theory developed and simulations, and Ludo has done a lot of work on this, how this can be used in more detail. The question how we can apply that is a different one because we need rather detailed measurements for many stations and so forth. But theory is there now and it can be used. So let's go to this part and talk about field observations briefly. I need my timing. So one application that is very close to us, like spatially in Potsdam, is one to an area where there was a test site for CO2 sequestration. I'm not going to talk about that, but we put an array close by to monitor with passive noise. And what I like about this application is that we actually have proper 3D seismic measurements that detected changes in the subsurface related to fluids. They in fact detected the CO2 plume that was spreading, and we see the location pretty precisely. It's below this reflector, where there's a catwalk above. So this is really nice, but you know what a 3D seismic survey means. So there were, 50 people busy for a month, driving around with huge trucks and thousands of geophones. So now we put out our geophones, and we had, in fact, 3 of them, and we could monitor continuously. Obviously, we don't see where these changes happen. We have to derive that from some other knowledge, but we could get continuous curves of the seismic velocity. So we could not just see that at one instance in time, but continuously. And here there are the black curves, or the black and gray curves. They show velocity measurements from 3 station combinations in that area. And the blue line that follows these curves pretty nicely is the groundwater level that was sensed at a well close by. The interesting thing here is, first, the correlation with the groundwater level, which actually shows that we are sensitive to the changes in the groundwater level. And due to the work by Eldert, we actually know that this is that our measurements are very sensitive to very shallow changes in the pore pressure. So this is supported well by theory, but we see these peaks here and here and here partially that we couldn't explain in the first place. So in the beginning, we only had data up to here, and I thought it's completely unreliable. That's like ages ago, but we always had these peaks. And only later, we discovered when we had a longer data set that these peaks always occur when the temperatures drop below 0. So these are the blue areas, and this is 0, and here's the temperature. So the ground is freezing with a strong increase of the wave velocity that we measure here, and afterwards with a strong decrease because the snow that is probably on the ground and all this water is penetrating down and increasing the groundwater level. Another application was published by Andres Barayas, and for more details you can talk to Piero, probably. So that's an application in southern Italy in a karst area environment that we've seen just before. And the interesting thing about this application is the detail of information that Andres retrieved here. The first thing is, again, the velocities, which is the black line, and this is the simulated water level. They agree very well. The water level was simulated from precipitation, if I'm not mistaken, and we have a pretty nice match of the velocity changes predicted from simulated water level and the actually observed changes. And interestingly, they also correlate very well with the horizontal displacement that was measured by GPS, because the increasing water level, of course, has some induces elastic perturbations in the subsurface, and there's a deformation that can be sensed by GPS. However, there are some differences here between the predicted and the observed changes, and these are rather systematic. So there was another type of information that was inferred here, because when it rains, the water doesn't rain into the groundwater; it rains on top of the surface. So there's another type of deformation that is induced due to the loading, which is basically the vertical displacement of the surface when the water falls on the surface before it actually gets into the groundwater level. And this is correlated with the vertical displacement, which is hard to see, with the vertical displacement sensed by GPS. And you have to interrupt me if I'm wrong here, but this is my understanding of this. Another application on groundwater level in a completely different environment in the San Gabriel Valley in California is very interesting, because it also shows a clear correlation between the observed water level in a well and the observed velocity changes in a completely different environment. Okay, we have seen these applications to Moon, so I will flick through here. This is an investigation that we did in Chile, where we observed variations at different periods. We have cycles per day here, and we interpret these as signatures of tides. And there are two posters about this work, and maybe we're actually wrong with our interpretation of interpreting this as solid Earth tides, because there's indication that these observations are rather, they're only possible when we're close to the shore. So in fact, there might be a huge effect of the oceanic loading effect or things like that. But what I want to show is this application here, which was done in 2003 by Yamamura in a dedicated facility. So it's in Japan, and there are galleries underground, and there's a receiver and a source that is fired every few seconds. They have an ultrasound pulse going through a distance of about 15 meters, and they measure the signals, they stack, and they obtain a measurement every 20 minutes and have observations over 1 year, which is a very nice time resolution to observe changes that might be introduced by tides. So, and this is the result. We have barometric pressure, which is not really interesting. The sea level height is much more interesting, because you see the typical tidal pattern. And you have superposition of the different tidal cycles, and you have phases where they interfere destructively, and you don't have too much tidal oscillations. And this is, in fact, the observation that is similar to what we observe with our monitoring. This is a differential travel time. So if the differential travel time is high, the waves are slow. If it's negative, then the waves are faster. And what we see here is first I mean, that's not really clear. It's only clear in the spectra, what we will see next. But we see this high-frequency oscillation, which go with a period of about 12 hours. But one thing that is really interesting is that whenever there's a phase of destructive interference of the oceanic loading, we have faster velocities here, and we have lower velocities, so higher travel time in these areas where they are fast, where there are strong dynamic changes, or where there's strong dynamic loading, strongly variable sea level. What is also interesting is the relative peak height, which is a measure of attenuation in this case, because we are not yet exploiting attenuation in our measurements with passive noise. So when we look at the spectra, we see this. We see lots of peaks of the oceanic tides, but we see this 14-day period that is actually related to an increase of the tidal amplitudes and a decrease, which I showed before. So what we just saw is when the ground is deformed dynamically in a strong way, the velocities are slower. And that's also something that we see here in this plot that we have seen before too. When the deformation is strong, the dynamic deformation, the velocities get slower. And then afterwards, when they cease, the velocity increases again. So maybe this is a related process, but the idea might be the same. This is work by a colleague of Hull, by Coda, who analyzed instrumentation in this dam during the Tohoku earthquake. And what he saw is a decrease in the velocity in this dam, which is pretty significant, and then a recovery. And the interesting thing, and we will see that later, and we've seen that before, is that this shows this linear behavior on a logarithmic timescale. So it is also some effect that is caused by the damage during the earthquake and subsequent healing of the dam. This is, again, earthquake-related damage that can be separated. It also follows a log linear trend, similar to laboratory experiments, but I won't talk about that because I would like to talk about the hydrological modeling that we did in Nepal in the next part. So there are some more results, and wherever you look during large earthquakes, you see a decrease in velocity, a decrease. It's never an increase, and recovery in the time afterwards. So we can reach pretty good sensitivity, precision with our measurements, and we can observe effects from various environmental effects, water, temperature, deformation, and healing afterwards. So let me talk about the hydrology and the interrelation between hydrology and earthquake damage. So this is work, as I said, it's done by Luc Elian and with other colleagues from geomorphology at GFZ. So this is a typical observation of earthquake damage in a bit more detail. We usually have some seasonal cycle that is imposed by the environment on our measurement during the earthquake, and this is the Chi earthquake in Taiwan. We have a drop, and then we have some increase, again, superimposed by the environmental changes. And the decrease in velocity is usually related, or it's assumed to be related, to damage in the rock, to defects that open, and to connections that are broken. And the recovery then is a process where the rock kind of goes back to equilibrium again. So now thinking of connections broken in the rock and cracks being opened, this will not only affect the seismic velocity. So there are other observations that are done after earthquakes that show a transient behavior. So this, for example, are normalized landslide rates for the same earthquakes that I've shown before, the Chi earthquake. This is the Chi main shock, and then after the main shock, these are the landslide rates. So at the time of the main shock, you of course have this co-seismic landsliding that is triggered by the strong shaking, but even after the shaking has gone, the landslide rates are strongly increased. So the landscape is basically damaged, and landslides are more easily triggered. That's why you have, for a couple of years, you have increased rates of landsliding. Some observations that is very common in hydrology is that whenever there's an earthquake, the permeability in boreholes is increased. And this can be measured by phase shift of tidal oscillations of the water level and the tidal strain. So one can infer the permeability in the borehole pretty easily. And it's always during earthquakes, it's increased and then it recovers again. So that's another transient observation. You can also observe hydrological effects in a river, because usually you have a rather steady river height, unless there are large rainfall events. But at the time of an earthquake, and this is again, this is the Gorkha earthquake that we will be talking about in Nepal, there's an increase in the water level in rivers. So at the moment of the earthquake, it drains a lot of water from the landscape, and that continues for a while, which is another transient observation after earthquakes. The classical way to model these effects combined on seismic velocities is to just assume a linear superposition. We have some environmental effect, which is mostly the hydrology, and then we have an effect of damage and healing, and this is just superimposed. And for the velocity change due to damage, quite often just an exponential recovery is assumed. And in this study, we went a bit ahead and did it a bit more in a sophisticated way, because these effects might actually influence each other. So questions that we would like to answer here is, can we track the co-seismic perturbations of the hydrological system? Can we see that actually during an earthquake, not only the velocities change, but actually the hydrologic system changes and the parameters that we can usually model the system with don't work anymore? So what we need is a velocity data set that includes co-seismic damage and hydrological observations. And we use, of course, need a consistent approach to describe both independently and then see whether there are some interrelations. The complexity, of course, that we have is aftershocks. We would like to have the effect of the main shock, but the aftershocks, they are not really the interesting effect, but they have to be described too. So what I want to show here is why we talk about Nepal. I will explain the geophysical setting and then go to the modeling. So this is an image of the landscape in Nepal taken by Christine after the earthquake. And everything that is light gray is landslide area. It's not all happened during the Gorka main shock, but there's a lot. So there was a lot of landsliding, and you see the landscape looks pretty scary, actually, if you think how much material is transported down all the time. But also, there's a strong seasonal cycle of precipitation. We have a clear monsoon season, and about 80% of the precipitation rains down between June and September. So there's a clear cycle that will likely induce strong changes in the subsurface. The geophysical data set is composed by an array that we installed in the Botekoshi Valley, which is kind of at the edge of the fault plane of the Gorka earthquake. The epicenter was over here. There was a large aftershock here, so we experienced quite significant shaking in this area. A closer look, we will be talking about an array of 3 stations that is installed close to the Botekoshi, so it's about 100 meters above the river that provides a consistent source of seismic noise. And we have between these stations about 50 meters distance, so they're very close, but we work in high frequencies, so that allows for good temporal averaging. So this is the noise correlation functions, and you might see there are pretty drastic changes here. And here, and here. So the waves slow down pretty strongly in these periods, which are the monsoon seasons. And the fact that you can see that with the naked eye here shows that we have a few percent already. And we work in the 4 to 8 hertz band at lapse times between 1 and 4 seconds. So the hydrological modeling. The typical model that is used is one where the drainage is basically proportional to the height of the water level. That gives an exponential decay of the groundwater. And then what we put in is the precipitation. At the top, we have some drainage that is governed by the hydrological parameters. And the height here, the height variations, are usually correlated with the seismic velocity. So this is the red model, model A. We have precipitation measurements, actually local precipitation measurements on site, and we can see the strong precipitation when the monsoon starts here and here in the gray areas. But there's precipitation before that does actually not affect the velocities, which are plotted here in black. So we have the black measurements, which are derived from the seismic noise. And if we try to model these very strong variations, because we talk about like 6%. We try to model that with the hydrological model. We see the red one, which does an awful job in fitting this shape. Because, of course, the velocities increase when the soil is drying, but they decrease immediately when the pre-monsoon precipitation starts. So this sharp decrease during the monsoon is not modeled here. So what is wrong here? And the model that Luc came up with, and this is something that is known in hydrology, that the soil above the groundwater has quite an important effect on how the groundwater is actually recharged. When the soil is dry, and we all know that, and it rains, the water just flows away. It doesn't go into the soil. It doesn't penetrate through. So when we have a dry soil, and we have a high groundwater level, before the monsoon starts, we have quite some discharge of the aquifer. And when then the precipitation starts, the first thing that it does, it refills the soil layer. So the soil layer gets moist, but still there's a decreasing drainage of the groundwater, and the velocities still increase because this layer goes down. When the monsoon starts, afterwards, the soil is wet, the water penetrates through the soil layer into the groundwater level, increasing the groundwater level, and the velocities decrease again. And then we also have this arrow here, which is kind of important, which is the transpiration. That is the drying of the drying of the soil layer due to the activity of plants that take out the water and evaporate it in the air. So we have an important effect of the soil layer here. The model then looks like this. We have inflow of precipitation, we have outflow by drainage of the aquifer, and we have transpiration that only occurs when the soil is moist. And this actually leads to the green model that we have here, which is derived from the antecedent index, which is really now hydrology, but it actually shows it is a model of the moisture in the soil. And we see that when we put a threshold on this antecedent index of the precipitation, we can see that whenever this reaches a certain threshold, then we have a connected system between the precipitation and the aquifer, and the water that actually rains on the landscape recharges the aquifer. So the gray areas are the ones when the environment is connected to the aquifer, and in the light parts here, it's basically the soil that takes up all the water and that also evaporates the water. So we have a two-stage system with connection through the soil or without. And this means that the soil actually acts as a gatekeeper for the groundwater recharge and for transpiration, so for the uptake of the vegetation. And this is quite a different system in the hydrology, and it's rather important because this is the Himalayas, and there are like about 800 million people living in the Indus, Ganges, and Brahmaputra basin, which are actually fed by precipitation that rains on this area. The system in this model basically says that the height of the water level, which is the discharge, depends on a parameter A, which is the hydraulic conductivity in the system. And we will remember that because this is a parameter that is actually influenced by the earthquake. The hydraulic conductivity obviously depends on cracks that we have in the subsurface and on the connectivity of the fracture network that drains the groundwater. So now let's see how this hydrological model actually performs when we look at the whole time series that we had. We calibrated this model on this time here because we excluded the first part, which is the one directly after the main shock. So the main shock was here. We installed the network, obviously, a few weeks later. And then we have a few aftershocks here. So how does the model perform when we look at the full time series. First, we have this modulated monsoon. We've seen it before. We have these aftershocks that are indicated here. And you see all of them basically in the velocity time series. But one thing that is important too is that the first monsoon here, the velocity change looks pretty different from the other three that we have. So here we have the 3 monsoon seasons, and we have a very steep decrease of the velocity during the start of the real monsoon precipitation. But when we look at the change in 2015, the decrease here was much more gradual, even though we know that the precipitation was very comparable. So we, of course, installed the precipitation measurements together with the seismic equipment, but from other places we have observations of the general precipitation pattern. And 2015 wasn't different in terms of precipitation, it's just different in terms of seismic velocity changes. Another observation is that our hydrological model is actually off on the long term, which might be due to the, or which apparently is due to the recovery after the Gorka event. And the fact that we actually saw pretty much damage in the landscape during the main shock, we can only establish with a permanent station that actually saw the main shock. And this is the Gumba station, which is part of the permanent network in Nepal, and have quite constant observations before the earthquake, and at the time of the Gorka main shock, we have a drop of like 5 to 3%. So also a pretty strong co-seismic change. And this is just a few kilometers away from our array. So what about the aftershocks, the damage? We also have to describe the damage to obtain a clue about the interaction between those. So we looked at the aftershocks and tried to model the drop and recovery of the aftershocks. And we have 4 of them which are of particular quality. The observations, we only use very short time series, time segments to not be influenced by the general evolution of the velocities here. And we can fit exponential models to these. The problem is we need an exponential time, a decay time that is different for all of these earthquakes. So we have like 1.6 here, we have 3.3 over there. So we need a few timescales, and that's of course not really satisfactory. When we model the time series that we would have to apply to correct for the aftershocks, it looks like this for the different timescales. And when we now look at the main shock to correct also the long-term decay from the main shock, we can obtain timescales between 80 and 1,200 days, these two. And it's, of course, not great to introduce more timescales in this for the main shock. So we thought about a possibility to model that in a consistent way. And one approach is the superimposed exponential spectrum, basically by Will and myself, that we used, because in this model we have the possibility to, or potentially it just works better. So we use this universal scaling relation with superimposed exponential processes, and the assumption that we do here is that basically all events trigger the same timescales, but just the amplitudes are different, because of course they introduce different amounts of excitation. So the goal is to come up with one consistent timescale. Just to show how the model actually responds to changes in the parameters, we keep the minimum timescale here at 1 hour, because that's kind of the time resolution that we have, and we couldn't measure anything below anyway. But we just vary the tau max, the maximum timescale, so the longest timescale of recovery that we can see in the system. And then we see that actually the decay takes longer, and also the amplitudes change. And we can fit the aftershocks that I've shown you before with this model. We have the exponential fit here, and for the recovery function, we fit the maximum time of recovery to all these earthquakes, and this is the same here. This 155 days is the same for all the aftershocks, and we have the misfit function up there. So now we can do that for the earthquakes, for the aftershocks, but we can also do that for the main shock, because it just assuming that it has a much larger time scale would probably model the larger recovery or the longer recovery better. And when we use only the aftershocks to infer the maximum time scale, we end up with something that is this 155 days. If we only use the main shock, we end up with something close to 1,000 days. And if we model both together, we will end up with a maximum time scale that is around 250 days. And let's see how that fits the data. The exponential is on top, and the three relaxation models with 155, 800, and 250 days are shown below. So now we can use these to correct our time series for the damage effect. We have these three models, which are shown here, and the data is in gray. And right, so the thing to note here is how we can, in fact, model the aftershocks and how we can correct the aftershocks. So the gray line is hard to see, but we have all these decreases here, and we have rather continuous curves for all these three models. So we can correct the aftershocks pretty well, and also the main shock recovery is pretty well modeled. I just wonder why these are so different here. Maybe I don't understand the plot. Good. So we have some idea of how to model the recovery of the damage and the hydrology. So now we can take the second step in the iteration and see how the residuals of the hydrological model and the damage model could influence our data. So do we have to modify the hydrological model after the earthquake, or does it still fit after the main shock? That's the question that we ask ourselves here. And what we see in this plot is the fit of the models that we have for these three different maximum relaxation times for all the 4 years of data that we have for all the 4 monsoons. And in basically all of these models, here or here or here, we see significant deviations. And when you look closer at this and think about where these deviations could come from, it basically boils down to the fact that there's too much groundwater in the system in 2015, right after the earthquake. So the idea is that indeed we've seen that the landscape changes, and is it possible to introduce a transient drainage parameter in the model to better describe the fit of the velocity data by the hydrological model? So we basically change this term, which describes the hydraulic conductivity in the subsurface, and we have used different timescales for this parameter. So how fast does a hydrological system actually evolve back to its original time period? And now this is a pretty busy plot, but let's focus on the right side here, which is hard to see from over there. But anyway, we have the initial model, and we have a transient hydrological parameter shown here. This means the system is much more permeable, and here it recovers to the initial permeability. And here we have the final model that fits the data quite a bit better. And when we look at the zoom in into the first part directly after the main shock, we see that we actually model this early part pretty well, and also the later part too. But the important thing is that we can really describe this lack of groundwater after the earthquake that we see in in the velocity data. And there's actually independent data that can support the fact that the hydrological system changes. So this is the stage height at the Barabise station, where we measured the height of the river, and it increases during the main shock. And then we have some fluctuations, but the fluctuations here, they are significantly lower than here in these two monsoon seasons. So the system kind of is equilibrating the precipitation much better because it drained a lot here, and the storage in the landscape decreased here, and afterwards, yeah, we have the post-monsoon decay of the stage height. So this is just the change in the hydrological system that we infer from this. So let me conclude. We have huge co-seismic and environmental changes at this location. The nonlinear effects in the subsurface relaxed after the first year. So that was these 250 days that we have as a maximum relaxation time. This is in agreement with landslide rates that were measured, because we installed the network thinking that it would take ages to recover, but that's not the case. After one monsoon, it was basically back to normal. The main shock and aftershock relaxation can be described by a consistent model with a single relaxation time, given this model with the superposition of relaxation times. The hydrological model shows that actually the soil is a very important agent in this hydrological system, with a kind of strong implications for water supply. We have a significant co-seismic perturbation of the hydrological system, and we can kind of monitor that. And considering a linear superposition of strong co-seismic changes and hydrological or environmental changes might actually hide some information and be an oversimplification. Thank you.